because we've just gone on to 1:30 now. Okay, so we might get started. So it's a real pleasure to introduce this year's Clay Fellow and Clay Symposium speaker. I have a few colloquial announcements, but I'll probably do that at the end of the talk. But now, Fabio, I'm going to give an introduction to Fabio, and also first I want to welcome Thomas Clay, who is attending the talk online. Thank you, Thomas, and we also want to acknowledge Thomas's family for their generosity in endowing the Clay Fellowship Program and enabling this lecture series to happen as well. And I'm sure they're going to be delighted to hear about Fabio's presentation today, because Fabio is going to be talking about searching for black holes from nearby to the Faraway Universe. Fabio has held joint BHI and Clay fellowships at the CFA since late 2019, and in his work he strives to combine theory and observations to study the unknown populations of black holes in the universe. He was born in the far south of Italy, which sounds very nice, and he completed his PhD in 2016 at the Scuola Normale Superiore in Pisa under the guidance of Andrea Ferrara. During his doctorate, he focused on studying the observational properties of the first population of black holes formed in the universe, and as a result of this, he was the first wave of recipients of the newly created IAU PhD Prize and the biennial Livio Grattan Prize for the best PhD thesis in astronomy. Congratulations, Fabio. And after that, Fabio moved to the United States, and he worked as a postdoc at Yale, where he collaborated with Meg Yuri, Priya Natarajan, and Nico Capilouti. And following a brief stay in the Netherlands as a NOVA fellow, he returned to the US at the CFA, where he's worked with many scientists and mentored 13 students. Fabio is also deeply passionate about science education and outreach. For example, he's authored 8 videos with TED. Oh, you should all go look at his videos on TED, which have attracted more than 12 million views combined, where he explains the science of black holes. He's also a regular contributor to the Scientific American and an organizer of a scholarship that funds the study of undergraduate students in physics from underprivileged and rural communities in the southern Italy. So I'm really delighted to introduce Fabio and hear all about his searching for black holes in the universe. Thank you.
This is on, right? Yeah. All right. Thank you, Lisa, for the introduction. Thank you, everyone, for being here. So today I will give an overview of some studies I've been doing in the past years at the CFA. And as you will see, the common theme is the search for black holes across space and time. So the talk is organized as a Redshift ladder. So I will start from the local universe and then reach the very early one. But before jumping into the science, I will start with literal Redshift 0 across the Charles River to tell you very briefly how my story with the CFA started in 2012 with a picture taken by Mark Palmer, actually, which has also a public service announcement. If you know where the ITC cup is, please bring it back, because we would like to restart. So I was a third-year undergrad student in Italy, and I had the chance to spend a couple of months at the CFA. And at the end of the summer, the ITC soccer match was in the plans, and they desperately needed a goalkeeper. So I was drafted not because of my academic or athletic capabilities, of course, but because they didn't find anybody else. And in the end, we won the match, but it was that summer afternoon that I really understood how much I enjoyed this place, not only for its incredible science, but also for its people. So today, after 11 years, I'm giving this talk mostly because a lot of people believed in me during these years, and to them it goes my thank you. So let's start from black holes, and we all know here that there is a zoo of black holes out there. from the very low mass ones to supermassive ones. On the left side, you see stellar mass black holes, typically up to 100 solar masses, depending on the definition, of course. This is the standard formation channel for black holes. We know very well how to form those. On the other end, you see supermassive black holes. These are typically found at the center of galaxies, typically above 10 to the 6 solar masses. And we know that how to form them, starting from smaller units, typically stellar mass black holes. But as we'll see later on in the talk, this growth process requires a very, very long time. In the middle, you see intermediate mass black holes, typically between 100 and 10 to the 6 solar masses. They are more challenging to be found, and they are typically found at the center of dwarf galaxies. So in this talk, I will mostly focus on intermediate mass black holes and supermassive black holes. To set the timeline of this story, this is a brief cosmic history of black holes. On the left, you see the Big Bang. We are now about 13.7 billion years after this event. The peak of black hole activity, the quasar peak, where we see a lot of supermassive black holes shining in the universe, happened quite some time ago, about 2 to 3 billion years after the Big Bang, while the first supermassive black holes, the most ancient that we are able to observe now, they are observed already less than 1 billion years after the Big Bang. While the first population, the first black hole seeds, so the first population of black holes, were formed quite earlier, typically around redshift 20 to 30, so a few hundred mega years after the Big Bang. So this is today's journey. I will start from very low redshift, and I will discuss the possibility of the presence of a supermassive black hole at the center of a satellite galaxy of the Milky Way, Leo 1. I will spend quite some time on this topic. Then slightly more distant, we will discuss a few projects with a couple of students regarding wandering intermediate mass black holes in massive local galaxies and in the Milky Way. Then we will go to the high redshift universe, redshift 6 and above, when I will present the discovery of still the farthest length quasar known, and a couple of candidates galaxies at redshift higher than 6 that you will see they are quite interesting still for several reasons. And then, in the very last minutes, I will briefly talk about black hole seeds, the first population of black holes. So let's get started from the redshift, basically 0. And I will tell you the tale of two galaxies and what one of them might contain at the center. So you see on the left a representation of the Milky Way. On the right, you can see Leo 1, a satellite of the Milky Way. So in this talk, I will present for the first time some newly acquired data from VLA, SMA, Chandra, and also HST archival, supporting the detection of the supermassive black hole. So we all know that the Milky Way has a 4 million solar mass black hole at its center, and if you place the system of the Milky Way in the M star relation, so a correlation between the mass, the stellar mass of the bulge, and the mass of the central supermassive black hole, you see that it's very slightly undermassive with respect to the standard M star relation. Now, imagine to keep the black hole mass basically the same, and instead it's hosted in a much smaller galaxy, about 1,000 times smaller than that. So as you can see, the black hole, the system black hole galaxy would be very overmassive, now 2 orders of magnitude overmassive with respect to the M star relation, if this is true, of course. So this scenario was suggested about a year and a half ago in this paper, in which they suggested the presence of a supermassive black hole of 3 million solar masses, basically Sagittarius A star, the black hole at the center of the Milky Way, but in a satellite galaxy of the Milky Way. And in this paper, they say that the no black hole case for all their assumption is excluded about 95% significance. So we said, well, let's believe this finding and let's see if we can observe this. So Leo 1 is a dwarf spheroidal galaxy at a distance of about 255 kiloparsec. Important for our tale, there is no star formation in the last 1 billion years, so it's basically a relic galaxy. And the core radius of the galaxy is about 250 parsec. Now, if we believe that there is a supermassive black hole at the center of this galaxy, and if you assume we realize the gas with the stars, you get that the boundary radius is basically is similar to the core radius. So the dynamical interaction, the dynamical sphere of interaction with the black hole is very large in this case. So if this is true, this would be the second closest supermassive black hole ever detected. So we made a model to try and understand if we can observe electromagnetically, of course, this source. Within the estimated boundary radius, there are about 100 kinematically confirmed RGB stars. Now, you take typical mass loss rates for RGB stars. RGB stars are red giant branch stars, so they are evolved stars. So you get low accretion levels, so the accretion model needs to be an EDAF, so advection-dominated accretion flow. And you can estimate, I won't go into too many details of the model, I just want to go to the results, but you can estimate an Eddington ratio, so a ratio between the accretion rate and the Eddington rate of about similar to 10 times higher than Sagittarius A star. So from this data, you can get an estimate of the spectral energy distribution, so how much the source is emitting at each frequency. And these said models in particular were taken by some models by Dom Pesce, who is also at the CFA here. And the 10 lines here, they are calculated with 10 different estimates for the Eddington ratio. Basically, what matters is that with reasonable integration times, this source should be kind of easily observed with the VLA in the radio, ALMA, for example, in submillimeter, higher energy Chandra. So this is all theory, but we actually got to try and observe this source. We got 30 kilosecond Chandra, and we found a very interesting source that it's 12 arc second away from the estimated dynamical center of the galaxy. Now, this source is well within the 3 sigma positional uncertainty estimated in the same paper about the dynamical center of the galaxy. So 12 arc second corresponds to 14 parsec. This is a very strong detection, it's a 5 sigma detection, and the gamma is about, the photon index is about 1.2, so indicates a hard X-ray source. Then we got radio and submillimeter data. The radio analysis was done by Genevieve Schroeder. She's a PhD student at Northwestern, who is also giving a talk today here. And the SMA data analysis was done by Mark Gorwell at the SMA here. So we got very strong detections that are coincident, of course, with the X-ray data. And in particular, we got a 9 sigma detection in the SMA. We think we found also the optical and infrared counterparts. This is archival HST data going from the optical from the near infrared to the optical. And before going into an overview of the current photometry that we have and why, in particular, we think that this is what we are looking for, I just wanted to highlight the fact that this observational campaign had a very large CFA footprint, also because the SMA and Chandra are both operated by the SAO. So thank you very much for allowing to do these observations. This is the current photometry that we have so far from the radio, submillimeter, optical, near-infrared, and X-ray. Of course, well before asking for all this data, we started to ask ourselves, what can it be? Why we are believing that this could actually be an interesting source. So probably this is not a transient source because we found XMM Newton observations of about 15 years ago, a much lower signal to noise ratio, but the flux in X-ray is basically the same, so it's probably not a transient. If it's not a transient, if it's not the supermassive black hole that we are looking for, it could be an X-ray binary, could be a background AGN. Regarding X-ray binary, probably is not a high mass X-ray binary because there is no star formation in the last 1 billion years. A high mass X-ray binary would be dead by now, or mostly. And it's probably a hard state, low mass X-ray binary because we have a radio detection. So regarding the possibility that this is X-ray binary, the data doesn't indicate. So if you place our source, which is always indicated in this talk with a yellow star, you see that the X-ray and the radio data are quite detached with the branch that you expect from X-ray binaries. This is a famous paper by Gallo in 2012. And in particular, if you run the numbers in the same papers, you see that our source is detached between 6 and 10 sigma, depending if you consider a single or bimodal distribution, from where you expect an X-ray binary to be. Actually, even more interesting, from my opinion, from my perspective, this is our source in the fundamental plane of black hole activity. So just a reminder, fundamental plane of black hole activity connects the radio, the X-ray, and the mass of black holes over a 9 orders of magnitude scale in mass. So as you can see, this source is quite close to Sagittarius A star, and it's not in the same region that you expect an X-ray binary to be. Of course, this takes into account the estimated mass from the dynamical measurement. So probably it's not an X-ray binary from their radio and X-ray detection. We also investigated quite for a long time the background AGN hypothesis, and these are templates actually taken from Martin Elvis, 1994, and updates, Sheng 2021. This is a radio loud and a radio quiet AGN templates. So what happens is that if you match the radio and the submillimeter, then the optical and the X-rays are too faint. If you match the optical and the X-ray, then the radio is too faint. We are aware that there are very large variations, of course, in AGNs, but this source seems to be, so the photometry seems to be about 3-4 sigma away from the median templates. And also the frequency of the peak synchrotron is not similar to what we are getting here. Actually, there are additional reasons to exclude a background AGN. The X-ray spectrum is quite hard, and usually this indicates a low Eddington ratio, indicating a more likely lower distance or nearby source. For sometimes we thought this could be like a Seyfert galaxy, but there is no apparent host in the optical images. And also, if you go from standard log n, log s diagrams, so these diagrams basically tell you the number of sources that you expect per square degree within a given, above a given flux, you get that the probability of a background AGN being like randomly about 12 arc-second away from the dynamical center is about 1%. So it's possible, of course, but it's not likely. We actually started to compare our photometry with that of Sagittarius A star. Our photometry here is indicated in with yellow stars again, and these are GRMHD simulations done by Ressler, and also there is some photometry for Sagittarius A star here. So as you can see, the photometry is quite comparable with what you get from Sagittarius A star, and the X-ray luminosity of the source is compatible with a Sagittarius A star mode in a flare state. Actually, we got some beautiful simulations by Angelo Ricarte, postdoc here, of course, from the Event Horizon collaboration. These GRMHD simulations were done with the parameters that you expect from this source, so the mass, the Eddington ratio, and the spin of Sagittarius A star, basically. And the 6 lines that you see here, these are different viewing angles, while the physical properties are the same. And as you can see, again, the photometry is quite compatible with what we are getting, except that we are underproducing the X-ray. So why are we underproducing the X-ray? Well, as Angelo explained to me, GRMHD simulations only account for X-ray emission within 100 gravitational radii, while most of the X-ray emission seems to come from larger radii. And this is also what we see in Sagittarius A star, and we see X-ray radiation up to the Bondi radius of Sagittarius A star. Actually, this is work that I've done in the last couple of days. We wanted to see if there is some variability in the source. So this is the infrared variability in the K-band magnitude for Sagittarius A star. And you see that typically over a span of about 8 years, you see a 2 magnitude variability. And this is the data that we have from archival data that we have from the HST. We just have a few epochs concentrated around 2006 and 2011, but it also seems to vary about 2 orders of magnitude, so 2 magnitudes. So this doesn't mean anything, of course, but it's a further indication. So the next step, probably, maybe, hopefully, the final step, we got some data, we got some time on the Gemini South. Unfortunately, we haven't been very lucky with weather in the last couple of months, and now we're waiting for the moon to get out of the way. But if we get the optical spectrum, we want to measure the redshift to exclude the background AGN, and also probe the continuum to see the physical and ionization properties of this source. Before concluding this first chapter, which was actually the biggest, the longest one, so don't worry too much, I wanted to discuss a little bit one possibility as why there is a supermassive black hole in Leo 1. And this is actually a gift that I've taken from the Goddard Space Flight Center. So the situation is that there is a very massive, supermassive black hole in a small galaxy. So this is a project that we are doing with Emma Weller, who is here, an undergrad student. The situation is that Leo 1 had a very close passage with the Milky Way about 1.2 billion years ago, a pericenter about 35 kiloparsec. So we try to understand with simulations if this true tidal stripping could have played a role in stripping part of the stellar mass and having such an overmassive black hole at the center. So we ran some simulations with Astrid, and this is something that I just want to present because I think it's interesting. At Redshift 2, we found several examples of galaxies that have a combination of stellar mass and black hole mass that are quite similar to what we observe with Leo 1. But if you go back 1.2 billion years prior, you see that the stellar mass of the galaxy was much bigger, while the black hole mass was very similar. So basically what happened between Redshift 3 and 2 is that this galaxy got completely tidally stripped by interaction with this cluster of galaxies. So this doesn't prove that this is the case for Leo 1, of course, but this is something that we thought it would be interesting to point out. All right, so let's go to the slightly more distant universe, although we are still in the local group. And I just wanted to present a couple of projects that I did with 2 exceptional students here at the CFA to discuss intermediate mass black holes in local massive galaxies. So, in the Milky Way, we know that there is a central supermassive black hole, of course, that could be up to 100 million stellar mass black holes just wandering around. Most of them will be very, very hard to detect. And what about intermediate mass black holes? Well, we know that intermediate mass black holes are the center of some dwarf galaxies. For example, this is one of my favorites. It's a 50,000 solar masses black hole at the center of RGG 118. So how is it possible that intermediate mass black holes could end up in massive galaxies, for example, like the Milky Way, or even more massive? Well, it's possible that the dwarf hosting an IMBH, an intermediate mass black hole, might have merged with a more massive galaxy and brought the IMBH with it. This is the formation channel that we mostly focus in these works. There are alternative, mostly in situ formation channels. And we know, for example, possible that the Milky Way experienced more than probably about 15 major mergers with galaxies that could have contained a massive black hole at the center. So this is I will first describe a project that we did with Emma Weller. She's a third-year undergrad student at the CFA, and also with Lars Sternquist and Yue Ying. She's a postdoc here at the CFA. Thank you for a lot of help with the Astrid simulation, providing also beautiful images. So let's start from some general properties of intermediate mass black holes possibly wandering in local galaxies, and then we will move to the Milky Way. First of all, most of the IMBH population seems to be sinking towards the center of the host. On the left side, you see that 90% of IMBH studied have long-term velocities towards the center. And in fact, the highest number density is found in the innermost kiloparsec from the center of the host. So if you want to find intermediate mass black holes, you should look towards the center of the host, like it was predictable. We also studied the magnitude of the velocity vector, basically the orbital velocities. And on the left, you see what is the distribution of velocities with respect to the center of the galaxy, so galactocentric velocities. The distributions are quite symmetric, around a typical velocity of about 180 kilometers per second, with a spread increasing towards the center. Instead, on the right, you see the distribution with respect to the local gas frame. Why is it important? Because this is ultimately the velocity that determines how much gas can be accreted onto the black hole. So these distributions are very asymmetric and skewed towards higher velocities, and also the mean in this case is lower, about half of the previous one. So in these slides, I will show you how the accretion rate actually depends very dramatically actually on the distance from the center of the host. So in this panel, the horizontal axis shows the time. These are time evolution plots. The left vertical axis is the distance from the center of the massive galaxy. The right vertical axis is the Eddington ratio. Again, how much the black hole is accreting. So after the orbit stabilizes, what you can see is that you clearly see that the IMBH is accreting only around the pericenter. So every time that the distance goes almost to zero, you see a spike in activity. These are things that we can see from simulations, basically. So what happens is that, of course, the density of matter is much higher, close to the center of the galaxy, and also it's possible that the intermediate mass black hole is passing through the disk because their typical orbits are very inclined. So if we look for intermediate mass black holes of this type wandering in local galaxies, these probably have a very low duty cycle, so it's not going to be easy to observe them. Since it's not going to be easy to observe them, we actually focus mostly on intermediate mass black holes wandering in the Milky Way because they are closer, of course, so higher flux. And this is a project that was led by Brian Seipol, another exceptional undergrad student here at the CFA, with also Ramesh and some other people. So for this project, we assumed a Bondi accretion rate. It depends on the density of the ISM, the interstellar medium, the velocity with respect to the ISM, and the sound speed. And we mostly focus on intermediate mass black hole of 10 to the 5 solar masses, because this is the mass range that you expect if a dwarf galaxy is falling into the Milky Way. So we modeled actually 5 realistic environments in the Milky Way, each with a different composition, gas density, and temperature. So this was actually a very long job done by Brian. So the different environments was molecular clouds, cold neutral medium, warm neutral medium, warm ionized medium, hot ionized medium. But what matters is that all the results that we will show here take into account volume fractions, meaning that, for example, the molecular clouds, they are very rare environments. It's very unlikely that an intermediate mass black hole passes through them, while hot ionized medium, they occupy almost half of the volume of the Milky Way. So this plot shows the accretion rates in physical units here that are categorized in the accretion from the 5 different environments that I just mentioned. From molecular clouds, they are the highest accretion rates because they are the densest environments, to the hot ionized medium here, lower accretion rates because it's the rarest environment, meaning less dense. And in any case, all accretion rates are strongly sub-Eddington, as you can see from this line indicating the Eddington accretion rate. Again, from this data, you can calculate the spectral energy distribution with the same code I mentioned before. This is calculated, for example, for 5 different Eddington ratio, from very low accretion here in yellow to moderately higher accretion in red. As you can see, the peak of the distribution depends very dramatically on the accretion rate. And now we're working also on selection criteria to select these sources from the optical submillimeter and X-ray data. But before going into the question, can we observe them in the Milky Way, we have to define what we mean by in-band observability. So assume for a moment that there are 10 to the 6 intermediate mass black holes of this mass in the Milky Way. In the paper, we never suggest any number. This is just for statistical reason. We just needed a large number to probe also the very rare environments, the molecular clouds. So assume that there are 10 to the 6 intermediate mass black holes of this mass and that we can observe n obs. So in this case, the in-band observability, for example, in the X-rays, is this number. So in the next 2 plots, I will show you just the X-ray observability and the radio observability, given the audience here and most of the interest. So these are a PDF, probability density function, of observed fluxes in different bands. This is the X-ray. So vertical lines indicate approximate sensitivities of several instruments. For example, in the X-ray with Rosita, an all-sky survey, you could be able to observe about 10% of these sources, mostly in the molecular clouds and the cold neutral medium. They are the densest environments. With Chandra, close to the sensitivity limit, about 30%. With Axis, maybe future probe X-ray emission, about 40%. Regarding the radio, I just wanted to point out that the case of the NG-VLA, the next generation VLA, is very interesting because this is the only instrument that we found able to probe actually the hot ionized medium, so the most common environment in the Milky Way. So if the NG-VLA actually goes into operation with a large area survey, of course, we could be able to detect about 60% of these sources. Before concluding this part, I just wanted to mention that consider a passage of one of these sources through a molecular cloud. Say that the molecular cloud is about 100 parsec diameter. This gives about 1 mega year of crossing time. This would be an event visible in basically every band, imaginable, from the radio to the X-ray. So this also gives you some hint about the fact that there are not many of these sources in the Milky Way, most likely. All right, so in the next 15 minutes, approximately 20 minutes, I will go to the very high redshift now. First to the quasars in the epoch reionization, and then to the first black hole seeds, the first population of black holes. So first of all, why are we interested in finding farther and farther away quasars? Well, there are many reasons, but let me tell you one that I think is important. Currently, the farthest very massive black hole, about 10 to the 9 solar mass black hole, was found by Wang in 2021 at redshift 7.6. And the farthest quasar, defined with a mass more massive than 10 to the 9 solar masses, should be detectable by redshift 9 to 12. At the same time, we know that the first population of black holes were formed around redshift 20 to 30. So pushing the frontier of the farthest very massive quasar detectable shrinks the time between formation and detection, and this gives us a lot of information on the properties of the first black holes formed in the universe. So in the next few minutes, I will tell you the story of what is still the farthest lensed quasar known to date. I was part of this discovery, and also we made some theoretical consideration after. So what is this? This is a very far away galaxy, a very far away quasar, a redshift 6.5. And what happens is that its light gets finds a galaxy close by, and basically for gravitational lensing you don't see you see a brighter image of the quasar and also multiple images of the quasar itself. And I just wanted to point out that there may be a new candidate by Eduardo Bagnados at redshift 6.4 still awaiting as far as I know Chandra confirmation. So when this source was detected at the end of 2019, this was the brightest source ever found in the universe, because we didn't know that it was lensed, of course, by then. It's lensed by a factor 51, so pretty much. And as you can see, this source stood out as pretty weird compared to other famous supermassive black holes or quasars in the epoch of reionization, because it's very, very bright, with an estimated mass of about 5 billion solar masses. So this is the spectrum that we actually took with Xiaoyi Fan at the Keck, and this is a beautiful spectrum, but I want you to focus actually in the apparently less interesting part of this spectrum, which is shorter than the Lyman alpha. What you can see here, and also see here in this inlet, is that you see a weak continuum emission here in the Gam-Peterson trough, where you shouldn't observe any emission from the quasar itself, because it's before the end of their reionization. So this is what led us to get HST imaging, and this is what we got. Basically, you can see that the central source seems to be asymmetric, maybe a double source. And here on the left, you see something that seems to be detached from the main body. So this G turned out to be the lensing galaxy, quite a small lens galaxy. And this is the best fit model, actually, which has been confirmed by many observations later on. The quasar is at redshift 6.5. The lensing galaxy is much closer to us, around redshift 0.7. And this galaxy, by chance, is in the same line of sight, and it's brightening, it's gravitationally lensing the quasar, so that the intrinsic properties of the quasar are actually much closer to the main distribution of quasar, with an estimated black hole mass of only 400 million solar masses. So based on this discovery, we actually made quite a convoluted lensing model to try and understand how likely is this source, and if we are missing some other similar sources. So I won't go into the details, but I will just explain you this plot little by little. So on the horizontal axis here, you see the log of the probability of magnification, so how much a source at redshift 6.5 is magnified. On the vertical axis, you see the probability that you have a magnification higher than a given amount here on the horizontal axis. This is our source with a magnification factor of 51. And at the time of this paper, but it hasn't changed much actually, this is the observed frequency of lensed redshift higher than 6 quasars. I was telling you probably they found another candidate. Also the number of quasars detected at redshift higher than 6 is increased. So this should have increased much. In any case, you can compute the probability in the lensing model assuming different parameters for the quasar luminosity function. Let's call this, for simplicity, model 1 and model 2. These are basic parameters for the quasar luminosity function. Without going into too many details, what you can see from this plot is that independently on reasonable assumptions on the distribution of quasars in the universe, you seem to be missing quite many quasars, especially at mild magnification. So if they are mildly magnified, it's more likely that you are missing them. So we call this population of quasars phantom quasars because they are quasars that are lensed at redshift higher than 6, but for some reasons we can't detect them. So why can't we? Well, there is probably a selection bias in photometric surveys, so how we select these sources. So imagine that there is a supermassive black hole at redshift higher than 6 that you want to select as a quasar. You can do a photometric survey, and to select this quasar, you need to have a very large dropout between frequencies shortward and longward than the Lyman alpha. So basically, from this part of the spectrum to this part of the spectrum, the dropout band, you need to see a very large drop. Now, the problem is that if you have a lensing galaxy in the middle, the lensing galaxy is adding some flux here, and this can create a problem in your selection criteria. So actually, this is a simulation that I did for the original paper with Shawi, and you can see that if the source was magnified not by 51, but by only 30, this source would have never been selected as a lensed quasar because the selection criteria would have been fooled by the galaxy, the light of the galaxy here in the Gunn-Peterson trough. So it's possible that high redshift lensed quasars are misclassified into low redshift galaxies. This we calculated that shouldn't be a huge amount of sources. I won't go into details now, but you can ask me later, maybe we can chat. Now, in the last 10 minutes, I just wanted to go to even higher redshift, first talking about a couple of galaxies and then black holes. So when you talk about galaxies, this kind of slides is always, it's needed, okay? So just allow me. So at even higher redshift, of course, the JWST is routinely discovering very far away galaxies. So the question now is, do these galaxies contain supermassive black holes at their center? A few weeks ago, there was a first detection of a 10 to the 8 solar mass black hole at redshift higher than 10, I think. Now I will briefly present the case. So this is these are the farthest galaxies with a spectroscopic confirmation. These are redshift 13. This is as of April 7 because with JWST it changes every day, basically. So I will briefly present the case of two very interesting galaxies that we discovered about 1 year ago, and then we will see what could power their luminosity. So these were two candidate galaxies at redshift 13, HD1 and HD2. These have been for a few months the farthest in the pre-JWST era. So I will present the photometer of just one. This is HD1, so H-band dropout 1. You can see the photometry here that is compatible, more compatible with a Lyman break galaxy at redshift higher than 12 than a passive galaxy at lower redshift. In this case, there was also a possible ALMA detection in the O3 line that has been disputed by a future a successive paper. In any case, this is what we found regarding to these galaxies, and this is the case also for many JWST galaxies that were found later. Basically, what you can see is that the number density of these galaxies at redshift 13, they are much brighter than what you expect from standard theoretical and empirical models at the same redshift. They are brighter by about 2 magnitudes. So the first thing that we thought is, are these galaxies lensed? This is actually a paper, a study that we did with Rui Zili, another undergrad student who might be here. And what we found is that at the current limiting magnitude with which HD1 and HD2 were imaged with the HST, there is only a less than 8% probability that they were lensed and that the hypothetical lensing galaxy was too faint to be detected. Actually, these sources were also imaged with the JWST. I can't tell you the detail because I'm not the PI, but there are actually very good news coming in the next few weeks or months. Weeks, probably. So in the paper, actually, what we proposed is that there are two possible explanations for the extreme brightness of these sources. One is that it's an extreme starburst, so it's forming a lot of stars at the same time. And the second possibility is that this is a quasar. So this is the possibility that I will mostly focus on right now because it's the most interesting to me. Regarding the quasar hypothesis, if you start from very simple parameters about a black hole mass of 100 million solar masses, basically accreting at Eddington, and you use standard quasar SCD, again from Martin Elvis, 1994, you see that the photometry of these two galaxies is very well fitted by these SCDs. So this is a possibility that we should take into account not only with these galaxies, but also with many more galaxies that JWST is discovering. Actually, in October, I think, there is a Chandra observation that is scheduled to try and understand if this source could host a quasar. So if it's a quasar, we actually expect about 13 X-ray photons, which is quite a lot, I would say. But if it's not a quasar, we expect a not detection in the X-ray. So this, I'm very looking forward to get data from Chandra about this source because it's a very interesting one and will actually help us understand if these very far away galaxies are hosting already supermassive black holes. Now, in the last 4 minutes, I will tell you a little bit more about the farthest that we can get with Redshift. So now we're basically at the beginning of the reionization, Redshift 20 to 30, when the first stars and the first black holes were formed in the universe. So what's the problem? The problem is that we have already observations of very big black holes of 10 to the 9 solar masses already less than 1 billion years after the Big Bang. So the problem is, how did they grow up so rapidly? If you start from a lower unit when they were firstly formed, when the black holes were firstly formed, you have 500 million years to form these very massive black holes. So there are two possibilities, basically. Either you start from a low mass seed or light seeds, or as they are called sometimes. These are remnants of POP3 stars or population 3 stars, the first population of stars that was formed in the universe. Now, the problem is that nature is funny sometimes. There are possible some speed limits on how fast a black hole can grow. This is the Eddington rate, of course. So if the Eddington rate applies, at least on average, on this growth, then this channel is basically impossible to pursue. It can't grow so fast. There are many models that allow for super Eddington accretion rates, especially in the higher redshift universe. So in this case, theorists are happy because we are happy because you can form these black holes also with low mass seeds. An alternative is that you could form these black holes by more massive black hole seeds, being already formed with a mass of 10 to the 4, 10 to the 5 solar masses. There are many models to form massive black hole seeds in the high redshift universe. And especially during my works, I focused on the DCBH, the direct collapse black hole scenario. So this is an antediluvian simulation. For me, this was done the last year of my PhD, actually, but I thought it would be interesting to show for some consequences that us right now. This is a simulation of the spectrum that that is emitted by a DCBH, a direct collapse black hole of initial mass 10 to the 4. 10 to the 5 solar masses, and this goes from basically infrared, this is some millimeter actually, to the X-rays. As you can see, during the time evolution of these sources, they are growing, they are shining, etc. And JWST and also partially Chandra, close to the brightest part of the emission, but certainly future X-ray missions should be able to observe these sources. So based on these simulations, we actually made several selection criteria for DCBHs. This is a paper in 2016. This is another paper that we did with Priya Natarajan and also Angelo Ricarte here at the CFA regarding colors of DCBHs. And if you are interested, two different papers actually coming out in the next few months regarding these selection criteria. So if you're interested in direct collapse black holes, let's chat, or you will be interested to hear about this in the next few months or weeks. Regarding X-rays, this is my last 3 slides. We also made predictions on the possibility of observing these sources. This is in a Compton-thin regime, so if the source is not very obscured in the high redshift universe. And in this case, also Chandra should be able to observe, with very long exposures, of course, should be able to observe these sources. Now, the problem is that if these sources are Compton thick, so there is a lot of material, obscuring material between us and the source, you really need future X-ray missions to detect these sources. This is what we pointed out in a white paper for the decadal survey, that only a combination, a synergy of different instruments from the JWST to next generation X-ray observatories to LISA, of course, will really help us in detecting the dawn of black holes, so the first black holes that were formed in the universe. Now, we reached the end of this talk. During this talk, we made like a long journey across space and time to see just some examples of black holes populations that are still undetected. So since I've talked about many things, instead of a summary slide, I thought it would be nice to give a visual representation, a little bit artistic, of the charted and uncharted populations of black holes out there. So here, it's a bit artistic, but you can see what is currently mappable with the most advanced telescopes at our disposal. This is basically with JWST and with Chandra in the X-ray and the infrared. Basically, what we can observe is we can observe very well all these massive quasars, supermassive black holes, maybe intermediate mass black holes up to redshift 1 to 2, and black holes, stellar mass black holes, literally in the local universe. But across the black hole horizon, there are certainly entire continents of black holes that we are currently missing, and we are looking forward to discovering them in the future. Thank you.
Thank you, Fabio, for a great talk. Questions?
Let's talk. I was wondering about the Leo galaxy. Did you exclude the possibility that that source could be a dwarf nova or an AMF, a critical dwarf?
I think we looked into that, and the radio versus the X-rays was very similar to the X-ray case. Yeah.
So it could be?
No, it couldn't be, because the X-ray versus radio is very different from what you expect from. Yeah, in the branch. Yeah.
Okay.
This is one of the checks that we did at the beginning. Yeah.
So again, going back to Leo 1, if the hypothesis is that Leo 1 used to be more massive and then it got tidally stripped with interactions in the Milky Way, do you think there's an expectation to detect like a stellar stream in the Milky Way associated with that stripping event?
Yes.
Or Gaia or something?
So the only problem that we think there is with that hypothesis right now is that in Leo 1 you would observe a different brightness profile for the galaxy. Typically, if you have a galaxy that is tidally stripped, you see that the core of the galaxy is still very bright, and only the external part gets tidally stripped. So you would see like a distribution of the brightness that gets cut. And in Leo 1, you don't observe that. So it's possible that this is not the case. As I mentioned, this is just a possibility to explain supermassive black holes that are very, very overmassive in dwarf galaxies. I am not aware if there is any tidal stream detected close to Leo 1. This is something that we can look for, possibly. But it's not that if there is a supermassive black hole that needs to be the way it formed. Maybe it was a very massive black hole that for some reason didn't, and the galaxy didn't grow enough, didn't merge. So there are many, many other possibilities.
Questions? I just want to open up questions from postdocs or students.
Again, about Leo 1. So I understand the original dynamical detection was based on modeling velocity dispersion. And, is it possible to do a significantly deeper measurement and get, measure RVs of individual stars?
Okay, so this is actually what I've been trying to do in the last few days. And so we have two epochs with the HST. And I actually did some blinking, and I made also some calculations. And the problem is that, so there is a little source here that I still need to fix a little bit the astrometry here. But I did actually a better video that I didn't include here, but I can show it to you later. There seems to be only this source that has a significant, very, very small change in the position between 2006 and 2011. The problem is that this thing is much farther away than Sagittarius A star. This is 255 instead of 8 kiloparsec. And the problem is that if you consider like orbital, like circular orbits, etc., you expect that the typical shift at this distance should be a 100th of our arc second, okay? Which I'm not sure it's compatible with what we are seeing here, so I still need to work a little bit on the astrometry here. But this is something that would really be interesting to do, yeah.
Yes.
In your high redshift galaxy candidates at redshift 13, you said if you used the simple parameters of a 10 to the 8 solar mass black hole at redshift 13, which seems even kind of pushing the problem even earlier, I guess. I kind of wondered if you could comment on like the feasibility of that, whether you think that's actually likely.
So at 10 to the 8 at redshift 13, if accreting at Eddington we should be able to observe it with Chandra. Yeah, that's why we requested the time.
Yeah, I mean, in terms of, do you expect there to be a 10 to the 8 solar mass black hole?
So from a growth perspective,
yes,
it's very challenging. It's not much more challenging than the 10 to the 9 that we detected at redshift 7. Because redshift 7, redshift 10-ish, there is not much time, and there is a 1 decade in mass. So it's basically as problematic as the other one, which makes theorists happy, because there is, we like to create problems.
I've been looking at this in simulations, so we should chat.
Yeah. Mm-hmm.
Okay, we've got time maybe for one more question. Okay.
This is really tough. If you add the mass of Leo 1 and the Milky Way mass, and then you add the mass of the black hole mass of Leo 1 and the mass of the Milky Way's black hole mass, do we all converge down to the same happy line? Because like one of them is lower and one of them is higher.
I don't know. I haven't tried, but I mean, would be interesting if it did.
Because if they eventually merge, then there's no problem.
Okay, I've got just a couple of announcements before we thank Fabio again and get back to our other activities. So we're taking Fabio to dinner on Thursday, so if you'd like to come, email me, special play fellow dinner, so I hope lots of people join up. It'll be interesting, and we'll be able to ask Fabio more about whether there is something in that circle or not.
Oh, you can't see it. Well, you can see it here though.
Oh, it is there.
Yeah.
Okay, there's going to be no CFA colloquium next week, April 18th. This is in recognition of the public school vacation week, so that parents can be at home if they wish to and don't have to miss the talk. The final talk for the CFA members will be April 25th, featuring T. Temin from Princeton, and Dr. Temin will be presenting brand new 3-week-old data Very exciting. So the information is embargoed, and that means we're not going to be able to stream the talks on YouTube. A Zoom link will be sent out to CFA members, but you have to keep it quiet for those people who are unable to attend in person. I encourage everybody to attend in person. It's going to be very exciting. Okay, thanks everyone. Let's thank Fabio again.